Welcome everybody to a new tutorial. Got a question from a subscriber asking me to discuss what type of loads can we expect on a single beam. So I'll start with an introduction on the type of loads you can get on a simply supported beam, for example, and then we will try to do a challenging example of drawing the shear force and bending moment diagram for an uncommon load. Let's see, what do we have today? So for example, if I have a beam, let's say the beam looks like this. Okay, I can have a concentrated load. Another beam like this one, I can have a uniformly distributed load. Another one would be this one. I can have a triangular load. Okay, these are the three loads I can think of right now. Just let's try to relate or to see how can we get these types of loads in a real life situation. For this one, this is the simple one. For example, let me draw it right here. If I have a beam like that one, and it's resting on a support like this one, and I'm having a column that goes down to this beam. Let's say this is a column and this is the beam. Okay, so the way we represent the load coming from the column to the beam is this way. So this is the free body diagram, basically the simplest form of drawing this problem. Okay, what about this one? Assuming that I'm having a beam that looks like this, okay, and let's say this is the beam, say it's a concrete beam, for example. Okay, and let's say that this beam is carrying a wall, a masonry wall, a concrete wall, so it looks something. I'll try to do it like this. So if it's a masonry wall, for example, like this one, the weight of the wall or the load caused by this wall can be represented by this. This is just one example, guys. Okay, the more challenging one is the triangular load. I can think of two examples. Let's say the beam that I have looks like this, and I have a masonry wall, but it looks like this. Something like this. Okay, so the masonry wall is not completed yet. For some reason the guys at the construction site stopped constructing the wall, so the best way to stop it is by creating an angle of 45 degrees like this one. So the load created by this unfinished masonry wall will look triangular like this one. Again, for example, if you are having a tank and it's filled with water, for example, and let's say this is my beam that is supported like this. The pressure of the water here is high and here is 0, and it's linearly changing. So that's another example. So these two examples can be represented by this type. Okay, the one example I'm interested in for today's tutorial looks like this one. Can you have a beam, a simply supported beam like this one, with a length that is equal to L, and the load looks like this? Okay, so this is my load. W of X. Is there a situation where we can find load, or think of a load that looks, or that can be represented this way? One of the only situation actually I can think of is if you have a roof. Let's say that you have a roof like this in 3D. Let's say this is your structure, or this is your building, or this is your floor, whatever. You have the doors here and windows and stuff, blah blah blah. But there are beams that go across the roof like this, and let's say it was raining, and what happens to this beam? If, and only if, you don't have adequate drainage that gets rid of the water, what will happen? It will start deflecting like this, and moreover, water will be trapped right here. Okay, so the weight of the water at the middle is maximum, and let's say it's like this, and for this portion it's gonna be less, and it's gonna become less and less and less, so it's gonna look something like this, and on the other side it's gonna look something like this. So I can represent it with the load looks like this. Basically, it's the shape of the load is the opposite shape, or the mirrored shape about this axis of the deflection. So my question for you guys today, let me erase this so I can make some room for the problem I'm gonna solve. My question is, can we draw the, or first of all, can we find the reactions at A and B? Can we find these reactions? And can we draw the shear and bending moment diagrams? So, question, find R, A, R, B, and or AY and BY, the reactions. And the second question, draw V and M. And for the fun of it, okay, where is max M plus the magnitude of this moment? Okay, first of all I have to define the load. This type of load can be defined actually a couple of ways. One of them, we can think of this load as a portion of a sine function. So if you remember your sine functions, goes something like this, goes like this. So let's say that my load is from here to here. So this portion can be represented by a psi function, or I can represent it by a regular function. So for this example, I'm gonna assume that W of X equals W naught, or actually let me correct this, it's gonna be 4 W naught multiplied by x over L minus x square over L square. And if you plot this function, assuming that, and these are the values we're going to use, assume that W naught equals 10 kip per foot, and we will assume that the length of the beam will be, let's say 15 feet. If you plot this, it's gonna look exactly like this shape. Okay, so let's go ahead and start calculating the reactions. Okay, we used to, or the way to do the reactions by transferring the distributed load into a single force that acts through the centroid. Remember, if I have a uniformly distributed load like this one, W and L, I can change this to do the reactions, or to find the reactions to a single force with a magnitude of W, L, and it's acting at the centroid. Okay, and for the triangular load, okay, I can transfer it to this, and if this is my triangle, it's gonna act somewhere in here, where this distance right here is L over 3, so it's 1/3. For our example, we can see it's symmetrical about the middle, so we know the location of the load should be at the center. But what about the value of the load? The value of the load can be found by integration. How can we do this? Okay, remember from calculus, if you have oh, that's a very bad drawing, I'm sorry. Remember from calculus, if you have a graph that looks something, for example, like this, and I wanted to find the area what I do, if I know the function f of x, to find the area, all I need to do is go from, let's say, x naught to x1, so x naught to x1 f of x dx, and I'll find the area. And in our example, the area under the load is basically the magnitude of this load. So let's go ahead. So if I do the integration from 0 to L, that's over the length of the beam, of 4 W naught x over L minus x square over L square dx, what I can do, I can pull the 4 W naught out of the integral, and now I have x over L minus x square over L square dx, and that, I'm not gonna do the whole thing, guys, you know how to do this one, but let's do just one more step. X square over 2L minus x cubed over 3 L square, and that's gonna be evaluated from 0 to L. And if I do this evaluation, I will have the final answer to be 2 over 3 W naught L. This is the magnitude of the concentrated load from the distributed load. So now I have a beam with a concentrated load of 2 over 3 W naught L. So the reaction here and the reaction here can be found very easily. It's concentrated in the middle, so half of the load goes to the right, half of it goes to the left, so half of that is 2 over 6 W naught L. Same thing here is 2 over 6 W naught L, or simply W naught L over 3 and W naught L over 3. These are the reactions. And if I used L to be 15 foot and W naught to be 10 kip per foot, I will get here 50 K, and here I'll get 50 K. Okay, that's how we get the reactions. First we concentrate the load, we try to concentrate the load, and the way to concentrate the load is to find the area under the curve. And since we have the equation for the load, which is 4W naught x over L minus x squared over L squared, we can integrate over the whole length to find the magnitude, and to find the location of the concentrated load. We've done it by inspection, basically. So let me erase now this part and jump into the second part, which is finding or drawing the shear and moment diagram. Okay, now we'll try to find the shear, force, and bending moment diagrams, or try to draw them. And this is a little bit complicated if we try to do it the old-fashioned way. So let's remember this. Remember, in one of the tutorials we discussed that EI, the fourth derivative with respect to x, can be represented by this equation. So that's minus 4W naught x over L minus x squared over L squared, and if I integrate this once, I will get the shear equation. So let me change this notation to this notation right here. It's gonna make life easier for us. So it's dv dx, because if I integrate this, it's gonna be v only. Okay, so let's try to integrate this once. So we'll have v of x equals minus 4W naught. We've done this before, right? We had x squared over 2L minus x cubed over 6 or over 3 L squared. Now we have a constant of integration C1, and if I integrate this, I will get the moment equation. You see what I'm trying to do here? I'm trying to get the equations and try to plot these equations. This is going to make life easier for us. Okay, this is a constant, doesn't change. This one becomes cubed, and 3 times 2 is 6L minus this one becomes to the fourth power, and this one becomes 12L squared plus C1x plus C2. Now I have these two equations, but I'm stuck with two things, the C1 and the C2. How can I solve for this? Remember from previous tutorials, we've done this before, and we use the boundary conditions. So what boundary conditions do I have here? At x equals to 0, I have 0 moment, and at x equals L, I have 0 moments. How many boundary conditions? I have 2 of them, and I have 2 unknowns. I think I'm ready to solve it. So I'm using the moment equation. At x equals to 0, this term 0 plus this term becomes 0, because this term 0 minus 0 multiplied by something is 0, and 0 times C1 is 0, and now we have C2, and the whole thing is equals to 0. Why equal to 0? Because that's the boundary condition. At x equals to 0, m is 0. From this I get C2 equals to 0. So this one is gone. Okay, I'm using the moment equation. So I have a 0 equals minus 4 W naught L cubed over 6L minus L to the 4 over 12 L squared plus C1L. Let's try to finish this one off. So it's squared, and this one is a squared. Nice. So minus 4 W naught multiplied by L squared over 6 minus L squared over 12 plus C1L. We have, of course, a 0 here, a 0 here. Let's do this the long way. So it's 2L squared. 12 divided by 6 is 2, 2 times 2, yes, and 12 is 1, L squared, and plus C1L minus 4 W naught. Let's keep on going down. Okay, now I see that this 12 goes with this, and we have a 3 here, and minus W naught 2L squared minus L squared is L squared over 3 plus C1L, and that's equals to 0. And if I solve for C1, I will have C1 equals W naught L over 3. That's my C1. Okay, let me write the two equations down. I have V of x equals minus 4 W naught x squared over 2L minus x cubed over 3L squared plus C1, which is this, and mx equals minus 4 W naught x cubed over 6L minus x to the 4th power over 12L squared plus C1 x. These are my two equations that I need to plot. I will leave the plotting until the end of the video or the tutorial. And now let's try to jump into how can I find the maximum value of the moment. Let's do another color here, so it's max M. Okay, what do we know about the location of maximum M? We know that M max is at V equals to 0. So whenever the shear is 0 for a simply supported beam, you will have a maximum moment. Okay? And that will make me do the following. Set V of x equals to 0 and solve for x. So I have a 0 equals minus 4 W naught x squared over 2L minus x cubed over 3L squared plus W naught L over 3. Now let's substitute W naught equals 10 and L equals 15, just to make this form simpler. So what do I have here? I have minus 40 and x squared over 30, that's 2L, 2 times 15, minus x cubed over, well, that's a huge number, 675, that's 3 times 15 squared, plus 10 times 15 is 150 over 3, that's 50. Okay, and let's rearrange this. We will have the following: 8 over 135 x cubed minus 4 over 3 x squared plus 50 equals to 0. Okay, we have this equation to solve. If you know how to solve it manually, good luck. If you have a calculator that can do this for you, that's great. I use Mathematica to solve it, and I got 3 values, of course, because we have it to the 3rd power. Had x equals negative 5.5, and I had x equals 20.5, and I had x equals 7.5. So if I have a negative value, of course this x is wrong. The beam length is 15, so it cannot be 20. The x cannot be 20, it's going to be outside the beam, so this one's wrong. And x equals 7.5, that should bring a bell to you guys, so that should ring a bell. What it says that 7.5 is 15 over 2. 15 is the length of the beam. So what this value is telling us that the maximum moment takes place at midspan, and that's what we should expect, because remember the let me redraw the beam quickly right here like this, and maybe that's not very nice drawing, but anyways, maybe you get the idea. Have the support here and here, it's symmetrical about this axis, or the middle of the middle of the beam, and the concentration was at the middle. So all of these are telling me that I should expect the maximum moment to be at the midspan. Now, what is this maximum value? Now I found what the maximum value is, but I need to find the number. What is Mmax? What I need to do is go to the M of x equation, use or substitute 7.5, and we get a value. And if if I do this, m of 7.5, I will get 234.4 cubic foot. Okay. So in the next segment, I will show you three things. One, the plot of V and M. Two, I will show you how to solve the x cubed equation to get the 3x's. And third, I'm gonna show you how did I calculate these m of 7.5. And 1, 2, and 3 are all using Mathematica. So bear with me. Okay, now we'll try to use Mathematica to plot the equations we got for the shear, force, and bending moment diagram. So let's define some stuff. Okay, here I'm telling Mathematica to clear all previous calculations and all variables, basically start a new sheet. So let's define the V function. So V of x, we had minus 4 w naught. Okay, I'm gonna just say it's w, and it's gonna be x squared. The whole thing is over L, I believe. No, it's 2 times L minus x cubed, and the whole thing is over 3L squared and plus WL, and the whole thing is over 3. Okay, I define the shear. I'm gonna define the moment equation, and the easy way is just to copy this and change a couple of stuff. For example, this is cubed and this is 6, this is 4, and this is 12, and I should multiply by x. Okay, now I will ask Mathematica to plot these two equations, but Mathematica, for it to understand how these things work, I need to define L to be 15, just don't mind the units for now, and I will define W to be 10. Okay, and now I will tell Mathematica to plot not this function. I'm going to use two functions on the same plot. The first one is basically V of x. The second one is M of x. The variable, of course, is x, and the minimum is 0, and the maximum is L. So I'm plotting from 0 to the end of the beam L. The variable is x, and one would say, what about the W and the L? I already defined in the line that L equals 15 and W equals 10. So let's cross our fingers and hope the whole thing is gonna work. Okay, it did not. Okay, that's a very good thing to do, to understand why it did not work. Okay, maybe I should change this to 15. Now I know. I cannot use these brackets. I should use parentheses. Okay, and this is L. Yes, here we go. Okay, so this is the bending moment and shear force diagrams. Okay, and we can, let me see if I can tell. Okay, if I right click and use drawing tools, and let's say if I want to trace a point, and how do I trace? Operations, no, maybe next time. I just wanted to know how to trace certain values. Maybe it's this thing, get coordinates, yes. Yeah, here we go. So we have at 7.5 the value is 1.014, but we're not at 7.5 exactly. There is a way of checking anyways. I'm just gonna get a rough idea. Okay, let's double check our answers. At x equals 0, the reaction is 50. It's shown right here. And at x equals 15, the reaction is, well, minus 50. So what about the maximum value here? Remember, the maximum value of the moment was 234.4, and it was at 7.5. So let's go at 7.5 somehow. So basically this is the graph, and now let's try to check our answers. Okay, I will ask V of 7.5. How much is it? 0. So the shear at 7.5 is 0, and M at 7.5 is 234.37. I hope that's the number, guys. Yes, that's the number I got. Okay, now let's go ahead and try to use the or use Mathematica to calculate or solve for the x where the maximum moment is. How did we find the 7.5? Remember, we had to solve an equation of the third degree. Okay, we had to set v of x equals to 0, so let's copy v of x for now. Okay, I'm gonna define it again like this. Copy, and I'm gonna say solve v of x equals 0 and solve it for x. Okay, and I want numerical values, and I'm sorry guys, I tend to jump around and using symbols, but I've been using Mathematica for a while. I mean, I'm not that expert in it, but bear with me. N is to change the fractions into just numerical values. Okay, so we have three values here. We have x equals 7.5, we have x minus 5.5, okay, and x is 20.5 basically, and we've discussed that x equals 7.5 is my solution. Okay, and the last one, I believe I've done it, how to solve for m of 7.5. Just type it like this and it will give me the answer. So this kind of loading is common, but not as common as the uniformly distributed load or the point load or the concentrated load or even the triangular load. But at least now you know a way of getting the reactions and drawing the shear and bending moment diagram for it.